Hello and welcome to another Senior Curriculum Inspiration proudly sponsored by Texas Instruments Australia. The Curriculum Inspiration series is designed to help teachers to develop strategies in the effective use of Texas Instruments calculators and software in the classroom with carefully selected and pedagogically sound mathematical activities. My name is Peter Flynn and I'll be your presenter for this session. Today we will be focusing on an activity entitled Learning Exponentially, and I'll be using the Texas Instruments CX platform for parts of the activity. And a big shout out to Chris Ierson, who's a Texas Instruments trainer who developed this activity, and I think he's developed an excellent activity. This Learning Exponentially activity and many more free activities can be found on the Texas Instruments Australia website by navigating to the web address shown on the screen. Once there, select the Teachers tab, then the Senior Curriculum Inspirations, select the state, which in this case is Queensland, and the course required, which in this case is Mathematical Methods. I've selected today's activity from Queensland Mathematical Methods Year 11 course. All the files for today's activity can be downloaded as shown on the top right of the screen. The components of each activity consist of a student worksheet, an accompanying teacher worksheet with very helpful notes in blue to help you to perform the activity with students, and also the important answers which are detailed in red on the teacher notes part of the activity. And accompanying that is a TI Nspire or TNS file for you and your students to explore throughout the activity. So in other words, it's a pre-prepared file that you can download and use with your students. The thrust of this activity is to try and determine what happens to the graph of an exponential function when it is transformed through either dilation, reflection, or translation, and what combinations of these transformations are what is known as homomorphic. Now, homomorphic is a fancy mathematical term. It's probably best in this setting just to colloquially describe it as a homomorphism or a homomorphic expression or function really is, it may look different, but it produces the same result. So in this investigation, we will use TI Nspire technology to visually and numerically explore these transformations, namely dilation, reflection, or translation. And so what you get on your TNS file is you get a series of pages which have been pre-prepared for you and the students to go through. So part A of this activity asks you and students to explore the function y equals b to the power of x, where b is a parameter. We will have a look at this page live in a moment. But on that page, there's two functions in the graph application. There's f1 of x equals 2 to the power of x, which is the anchor function, and f2 of x is b to the power of x, which contains that parameter b, which can be altered. And the purpose of part A is to explore what happens to the points on the curve as the value of b is changed. So the values for b will change according to the slider, which you can see on the screen there. It currently says b equals 9. Values for b range from 2 to 10, and 2 points are identified specifically to help understand what is going on. The movement of these points may be considered in the x direction or the y direction, so dilation away from the x-axis or towards the y-axis. So this activity helps to build, hopefully, good language skills for the students so that they can describe transformations accurately and mathematically correctly. We can also use the swap slider to toggle the direction, as I said, dilation away from the x-axis or towards the y-axis. And so when students and yourself look at question 1, you're asked to consider a series of questions along the lines as the parameter b is changed from 2 through to 10, describe what happens to those anchor points 1, 2 and -1/2 by consideration of the y-coordinate. So in other words, how is the y-coordinate changing as the value of b changes? Which points, if any, are invariant, which means the point remains the same despite the value of b changing. Describe what happens to those two anchor points by consideration of the x-coordinate. Describe what happens to the shape of the graph as b is changed, and identify any asymptotes for each of the graphs. So what I might do just at this juncture is to get out of the slideshow briefly and then go to the page that I've been talking about, page 1.1, and let's see what happens here. So we've got a live slider which currently shows us that b equals 2. We've got our anchor graph in blue, and what we want to do is we want to change the value of b and note what effect that has in relation to the graph of f1 of x equals 2 to the x. So all you need to do is just make contact with the slider and just start clicking on the arrow. And what you'll notice there is that as we can look at the first question there. So for the point 1, 2, for example, as b increases, what do you notice about the y-coordinate? Well, the y-coordinate is increasing. That one is. Then you, and the reverse is true for the point -1/2. So let's look at that, and you can see that the reverse is happening. Which points, if any, are invariant while we're changing the value of b? Well, hopefully you've noticed that, and the students will notice that the y-intercept 0, 1 is the point that is invariant. What we can also do is this mysterious slider, which is a fantastic innovation actually, enables us to swap the direction of the dilation. So what we're looking at the moment is away from the x-axis. But if we click on the swap slider, we get a different viewpoint, and we're looking now at dilation towards the y-axis. So make sure that you get the students to focus in on the direction of that arrow there. So what you're seeing in effect is that all the points on the blue graph are dilated in a particular way to form all those points on the corresponding red graph. And so at the end of the 1.1, you want students to be able to answer the question, well, describe what happens to the shape of the graph as b is changed. And so as b increases, the graph is dilated towards the y-axis, which is also parallel to the x-axis. And the other thing you can do is you can start to talk about the behavior of these exponential graphs as x gets big in the negative direction. And what you can do is if you press Control T, what happens is you can add a table of values, and then what you can do is then just through use of your arrow keys, just move up, and as x gets big negative, you can look at the behavior of the function, and what's happening is it's getting smaller and smaller and smaller. It's approaching 0. So we can conjecture from that the asymptote, the horizontal asymptote, has equation y equals 0. Pressing Control 6 removes the table of values, and Control 4 enables you to show a split screen. And that's what's been shown there. Now, the next page, which is probably about the last one that I'll talk about in depth before just giving you a brief overview of the remainder of the activity, is our anchor function there is f1 of x equals 2 to the x. And what we're doing is we're looking at the effect of c on the graph. So in other words, by changing the value of c, what effect have we got in transforming the blue graph to the red graph? And we change the value of c. And what you'll also notice that moving with the value of c is this accompanying horizontal line, which has been inbuilt. And it turns out, of course, to be the equation of the asymptote. And the equation of the asymptote in this instance is as x gets big negative, the 2 to the x disappears and you end up with y equals c. But the other very, very nice feature of this page is if we activate the show slider, it shows us that each point has been transformed by the same distance in moving from the formation of the blue graph to the formation of the red graph. You know, that horizontal segment, no matter where you are, that distance is the same. It's invariant. And I think that that's a really powerful demonstration for the students. So in essence here, what you see here is that the shape of the graph's not changed. There's no dilations. The location of the graph has changed. The graph has been translated parallel to the y-axis by quantity c from the x-axis. The hide and show slider is fantastic. Make sure that the students understand why there is a horizontal asymptote and how to locate it. And you can ask a nice question also along the lines of, for what set of values for c does the equation 2 to the x plus c equals 0 have solutions? And what you'll find is that that will be the case when c is negative, all right, when c is negative. So that's given you an overview of the first two parts of the activity. And what I'll do now is I'll focus back in on the PowerPoint and just talk very briefly about the remaining parts of the activity. So it goes on to look at exploring y equals 2 to the power of x minus h. So there's two functions there in that graph's application. The anchor graph is 2 to the x, and then your parameter is h, and so f2 of x is 2 to the x minus h. And what you'll do there is you will change the value of h, and hopefully you and the student will note that the shape of the graph isn't changed. There's no dilations. The location of the graph has changed. The graph has been translated parallel to the x-axis by the quantity h from the y-axis. And the horizontal asymptote is the same for each graph, y equals 0. In other words, there's no vertical translations. And also notice there that that show slider will also give a very powerful indication that all the points on the blue graph have been all translated parallel to the x-axis to form the new graph, which is in red. That's a new set of points. Then part D asks students to explore the function y equals 2 to the power of mx. And there are three functions available to you on this page, and the show hide slider in this instance can be used to reveal the graph of f1 of x equals b to the x. You can change the values of m and b just by clicking on those sliders. And what we're trying to tap into here is this idea of a homomorphic representation. So in this instance, we're comparing 2 to the power of mx with b to the power of x. So the location of the graph is unchanged. The shape is dilated towards the y-axis. The dilation is by a factor of 1 on m parallel to the x-axis or towards the y-axis. Again, the y-intercept is invariant. And when you do compare 2 to the mx with b to the x, hopefully students will note that b equals 2 to the power of m, and that a pairing such as m equals 3 and b equals 8, because 8 is 2 to the power of 3, produce the same transformation. And you can ask students to find other pairs of values. For example, m equals 2, b equals 4, m equals 4, b equals 16. That's tapping into b equals 2 to the power of m. Next one is part E, exploring the graph of a times 2 to the power of x. And there's 3 functions also in this page, and the show hide slider again can reveal the graph of f1 of x, which is a to the power of a times 2 to the power of x. And what students are asked to do here is explore values of a and h for those graphs of 2 to the power of x minus h and the graph of y equals a times 2 to the power of x, a times 2 to the power of x. What we want students to notice here is that when you equate the two, a is equal to 2 to the power of negative h. And we want to get the students to determine values for which the graphs are homomorphic or the same, explain the outcome, and identify any limitations for the comparison. Also note here, folks, that if the students make a less than 0, the graph is reflected in the x-axis. So that's a nice little offshoot of this page. And given that a equals 2 to the power of negative h, then pairings like h equals 1 and a equals a half, h equals negative 1, a equals 2, h equals negative 2, and a equals 4 can be noted. We also look at situations where we can combine transformations. So going to page 6.1, 6.1 is a blank page for students to explore the problem which is expressed there on 6.2, and it's question 8 of the activity. And this is where we bring everything together and combine the transformations. Now, the encouragement that I'd like to offer here is I'd like the students to try and solve the question 8 and question 9 graphically rather than algebraically. Algebraically is certainly possible through the use of simultaneous equations, but it's nicer to be able to build the function up, knowing how the values of the parameters, or how the values of the parameters affect the behavior of the function. So, for example, in question 8 there, students could note that c equals 0 because now the graph of g of x, y equals g of x, that's the red graph there. They could note that c equals 0, so they could start with f of x equals 4 to the power of x. They could then say, oh, okay, maybe I need a reflection in the y-axis, so then f of x equals 4 to the negative x. And then they can put points on the graph at x equals 0 and x equals negative 2 using the point on feature. Then students will notice that a equals 1, and then they can change the value of m until they get a value of negative a half. And I think that that's a really powerful way of solving such a question. And question 9 should be tackled in a similar vein. By all means, after undertaking a graphical approach, certainly work through with the students the algebraic approach. Now, just in finishing, to put a point on a graph, it's a matter of just pressing menu, then geometry, then selecting points and lines, then selecting point on, clicking on the graph, and then just clicking a couple of times on the x coordinate. You can put this point anywhere on the curve, then double click and then just change the x coordinate to the one you want. So for example, in this instance, negative 2 would be good, and it would just take the point up to negative 2, 4. So this is what I've offered here. I've just talked about that. So choosing simplistic values for the parameters so that the students may develop the solutions using a sort of a quite sophisticated, quite smart guess and check approach. So that's about as much time as I have for you today. I've hoped you've gained some useful ideas that can be used in your classroom to inspire your students from the Curriculum Inspiration session. That's all we have time for today, so please visit the Texas Instruments Australia website for more free activity lessons that make students or encourage students and yourselves as well to explore, discover and visualize mathematics through the Texas Instruments technologies and for when the next curriculum inspiration is scheduled. So it's goodbye from me, and we hope that you got something out of it today, and hopefully you'll use this activity successfully in your classroom. Thank you. Goodbye.